Okay, unmuted. You can see the board, I assume. So when we started this thing, there was a solo board, which I really liked because it was really small and it was surface mount, and I could use it in a bunch of projects. And Dr. Ting said, why don't you just put the module connector on it and call it a day? That was a year ago. So, Brad and I wrestled with that damn board. It's very finicky on power up reset. And most of the data sheets show you just using a simple RC network because it's voltage level triggered. But the thing would flash like 1 out of 20 times. It was just horrible. So I redesigned the board and I put the plug in. So obviously the new boards will be programmable. I gave up, but I did actually this is version 4 of the board. I had a version 3 where I think I may have fixed it, but I started thinking, do I want to spend it? One of these board spins for the parts and the stuffing and everything, it's like $1,200 bucks. It's a lot of money. So I didn't want to take the chance that I didn't get it. So I just said, screw it. And I did version 4, which is a plug-in board. So we can move forward. So yeah, you can see like right here, the little board was about 1/3 of the size of this thing. So what we're going to do is we're going to run over to the schematics. And okay, so let me talk a little bit about the board a little bit. So you see these 3 holes right here? There is basically you take a piece of piano wire and you make a whisker, and use a 440 nut, screw it on there, and when the whisker deflects, it makes contact in these posts. So that's one sensor. These 4 connectors here, you can just put an LED and a photo Darlington in there, and that's the robot's eyes. So he has eyes that go sideways, eyes that go forward. The robot also has long-range sonar. So I developed my own sonar using the piezo electric transducers with the separate transmit and receive. And they can see out about 20 feet, and they can see within an inch of the sensor, which is extremely good for a robot. Back in the old days when they used the Polaroid sensors in the 90s, the Polaroid sensors had a dead zone of like 6 inches. So if the robot got too close to the wall disappeared. Not good. It's got a speaker and a microphone, so we can hear it. We're going to be using my Whiskers software that I developed for my Whiskers robot. That includes all the musical notes, so you can sing songs with it. It has many different sound effect words like laser, bird call, and all, a half dozen of those. Dr. Ting has got most of those words working in the new eForth that is downloaded to this processor. Brad has spent a lot of time porting Dr. Ting's eForth to the ESP, and he's got that working really well. So it's eForth that's written in C is downloaded, and so use a C compiler to create the 4th kernel that you download to this thing. It has a serial port, of course. Got a power connector. It's got an inertial guidance chip in it. So it's got, it knows, it can have electronic compass. So it knows all the different, from 0 to 359 degrees. It's got accelerometer and an inclinometer. So, it's going to know when it's not on flat ground, and if it runs into something, it'll detect that. Let's see. It's got a an SPI expansion port. So if you want to plug in an SPI board, connect an SPI board to it, you can talk to that. So you could add a vision board or something like that. So let's go into the schematics. Alrighty. So here's the that's basically the process. I did this in Eagle 7, and which I have on my PC. So you can see we have the in the ADC, we got the 4 eyes coming in here. I do monitor the current in the motors. The motors are the speed control is using pulse width modulation, but we monitor the current. Now, what's interesting with that in a robot, and you notice there's 2 current inputs. There's the left side and the right side. If you hold the wheel on the robot, the robot can sense it and actually react to that. Or if the body gets stuck and none of the sensors see anything, it can sense that and it can do behavior or an instinct on that. So its whole body is actually a sensor. Oh, I did put an SD card on it, and so
did you attach the stuff the right way around this time?
Yeah, I turned it around. I probably turned it 360 degrees though, you know.
I'm just teasing, Don.
No, it's good. I do shit like that. Oops. Yeah, so the serial port comes in here. The CS Mag XL, that's the inertial guidance chip. I have 2 auxiliary motor ports. So these are half bridges. What you can do with those is you can hook up a hobby servo and do, at 1 kilohertz, you just do, as you change the pulse width, the motor changes its angle. So you could put the sonar on 2 hobby servos and have a pan and tilt, for example. Okay, so this is a power supply. It's a switcher. I'm generating 5 volts, and also I'm generating 10 volts for the sonar right here. This is the speaker. Driver, just a FET. Single point ground for when I finally tie the analog and ground together. So I have separate ground. So the analog is 2 op amps that amplify the sonar signal. This is the H-bridge design. I try to keep it cheap and simple. So what I did was I used an open collector inverter to increase the 3.3 volts to 12 volts to drive the FETs. And it's a P channel on the top, N channel on the bottom. So there's dual channels there. These are the op amps. So we have this current sense resistor in the leg of the H bridge, and that goes to an op amp that will amplify the voltage. You'll notice it's a non-inverting op amp. Okay, so this is the sonar. Now, this is an interesting circuit I developed in the 90s. So you have 40 kilohertz sine wave coming in here. And what I want to do is, all I want to know is I want to know the peak amplitude of that 40 kilohertz sine wave. If there's nothing there, the sine wave will be really tiny. If there's something in front of it, the closer it is, the higher the peaks are. So what this circuit is right here, notice there's a diode. So that's basically, allows current to flow this way, but not back. So when the sine wave 40 kilohertz goes up and goes back down again, it's a peak detector, and so it charges up the cap. So this RC time constant allows you to set how fast it charges, and then there's a load resistor, which is either 10K or 100K. I got to play with this circuit. I haven't played with it in 20 years, so I'll be adjusting these values probably. But anyway, this allows the cap to, after it gets charged with a peak, it allows it to decay. And this goes into an ADC. This is actually the microphone right here. This is the sonar down here. So we have two of these op-amp circuits. These are your half bridge auxiliary. So this would be for your hobby servo motors. Let's see. These are those connectors I showed you for the eyes, and it's just simply you can not install the connector and just install an LED and a photo Darlington, or you can put the connector on and you can remote the eyes somewhere in your robot. So there's just pull-up resistors there. And this is the inertial navigation chip, and we got that. Yeah, this is the SD card, which hopefully I got on the right way this time. Oh, and Brad, this is going to be my solution to the reset problem. This is a reset chip. So basically, with this RC time constant, it holds reset low during power up, and then after a delay, it goes high. This is a more, and this is a reset button down here. This is a more reliable microprocessor reset, power on reset circuit. I left it in this design. It shouldn't need that circuit, but I already designed it, so I left it in.
Yeah, couldn't hurt.
Yeah. So that's basically the board. All the parts are going to the fabricator, the PCB stuffer in Santa Ana, California. They'll be there like Monday or Tuesday. By Tuesday, he's making 35 boards, and so hopefully about a week later I'll get 35 boards. I'll check them out hardware-wise, and then I'll send some boards out. I'm not gonna check every little I/O, but I want to at least make sure they're programmable, and the power's correct, and I'll check a few things out, and then I'll send some boards to Brad and Dr. Ting and anyone. We've sold 8 boards in the group total. Dr. Ting bought 2, so there's probably around 5 or 6 people that paid for the boards. So if you paid for the boards, you send me an email at donaldargolding@gmail.com with your address. I won't be sending you boards right away until we check all of the hardware out, unless you want me to. So
if one wants to get an early board as soon as possible, can you take PayPal or Krugerrands, or what would you like?
American Eagles. No, PayPal's fine. I have a PayPal account. I will be donating boards to the FIG group, at least 5 to 10 of them, I guess. I want to support the young guys. He's on here. Chen, you're on here, right? And
yeah, I'm here. Hey,
yeah,
Don.
I want to support your group, so I'll donate a couple of boards over there. Okay, here you guys are gonna love this. Here's some big news. So, to those that don't know, I moved to Florida I work for a company called Made in Space that is totally amazing. Do I have time for a 2-minute video or not? Kevin? Oh, Kevin.
Well, is it the same 2-minute video you've been showing?
Well, there's new people on, I think. It's okay.
Yeah,
Anyway,
show it. Go for it. Hit the go button.
okay.
2 minutes.
So just for those people that don't know what I work on, I am working on the computer for what's called the Argonaut robot. And it's the coolest freaking project I've ever worked on. So this is an autonomous spacecraft, and it's going to 3D print a solar panel that is 1 meter wide, which is about 3.5 feet wide, and about 100 feet long, or 30 meters long. And then it's going to use a robot arm to pick up the machine, the 3D printer that does that, flip it over to the other side, and then print a second beam. I am designing the space-based computer for the 3D printer and the robot arm control system. I'm the chief engineer working on that, and it's totally FPGA. It has to meet 100 rad radiation requirements, and minus 55 to 125. So it's a very interesting project. It's I'm learning some new stuff about designing space electronics, which I'd love to learn new things. So the robot arm, so there's simpler engineering ways to do this, but the company wanted bragging rights of using a robot arm to manufacture something in space. So that's why it's a technology demonstrator. So future Argonaut robots will be manufacturing things in outer space. The company has all kinds of different manufacturing things going on. We got a program to extrude fiber optic cable in space, which is so pure, it extends the range and the data rate tremendously from those cables made on Earth. They have a 3D printer that uses arc welding to make, metal structures. It's when I walk through the lab here at Jacksonville, Florida, it's just amazing. It's like walking into Tesla's lab or something. And I designed 2 boards in the beginning, and both those boards are being used on a lot of different equipment here, which makes me feel good. The last thing I want to just tell you about is we have what's called a software COP, and it's a community get-together kind of thing. Let's see. And I open it this way. I'm promoting forth within Made in Space, and I have about 5 engineers interested. So some of these boards are going to go to Made in Space engineers. So I open it up like this. I said, okay, imagine Made in Space has 100 robots that are doing mining and construction out at Pluto. Are you going to if we have to do a code change, are you going to create the C code, compile it, create a binary, and send it over a wireless link that far out, which is 9,600 baud? It'll take a month to upgrade all 100 robots. What if you could do that in minutes or seconds? So I'm going to show you this is what I said to them. I'm going to show you a language you can do that with. It's called Forth. So I spent about an hour and a half with these guys going through Forth. I used G-Forth, and I shared my my screen with them, and I showed them how you could do. That's our president right there, Andrew. I showed them how you could do deferred word. So I said, you could have this compiled application and some, driver word at the bottom. You got to change it. Well, you just do a deferred word. So you just send up the source code, which is, 20 characters of code, and it instantly incrementally compiles it on the robot. And then any of the code that is calling this word will call the new code. So we used deferred words and forth. And then I also showed him using create does. I didn't show him, I didn't get into the basics of forth. I wanted to show him the most powerful features of forth. So I showed him how you create a word called array that defines an array. And you give it a parameter of how large the array is, and then you give it a name, and now you can, access to the array with the name. One of the things I did with the create does is I compiled the size of the array. So then I had two words called read array and write array, and it got the size of the array. So it's a counted string in some other languages. And so basically made a counted string. And I showed him how, we're creating a language. Forth is a meta language. You create other languages with it. That's its power. So anyway, I have about 5 or 6 people here at Made in Space, and when I get the robot boards done, I'm gonna propose that Made in Space do an educational outreach with them and put their name on it, and try to get them in like tech ed, labs in high school and junior high. So I think that there'll be really powerful educational boards. We get young people programming in Forth, and I have this high level language for robotics called the Triune OS. And forward 10 feet stop is actual code, right? It's simple code. So we had kids back in the 90s. I sold 2,000 of these Whiskers robots. We had 6 kids a day, 6 periods, and then every semester, there'd be more. So, 3 semesters. So you had 18 kids. Well, you had 6 per day times 3, 18. So you had a lot of kids learning programming with Whiskers, and they only did it in 10 hours. So there were 10 one-hour tasks, and there was always a test after each task. They had to solve a problem. So when they learned how to do, in one chapter, constants and variables, then there's a task that they had to use constants and variables with. They learned how to, make loops, do loops. And at the end, there's a task where they had to make a box using a do loop. So I think this robot could really get Forth going again. And we're making everything open source. It's going to be open hardware. Schematics will be out there. Somebody wants to start a company and make boards, knock themselves out. It's kind of like my legacy, it's what I'm going to leave on Earth when I pass. So.
Say, Don, a question about Made in Space. So you've relocated to Florida. Do they still have a presence at Moffett, or did they move fully to Florida?
So most of the people did move from Moffett to Florida. When I started there was over 20, maybe 24 engineers at Moffett. When I left, there's probably 12. They encouraged engineers to move to Florida because this is where the action is, and I needed to be here. I felt like I was, locked up in my room, right? I couldn't interact with all these brilliant, guys, making all these cool machines. I needed to be out here. Oh, and by the way, Florida has no income tax, so 12% of my salary I get to keep now. California used to take it. And the cost of living here is 20% of what it is in Silicon Valley. I saw houses. Now these are distressed houses in not great areas, but under 20 grand for a house. If you get a nice house, you're going to spend, 150 or so. A hamburger here at a place called Steak and Shake. You get a really great burger, fries, and a Coke for $4.95. Gasoline is $2. It's a lot of people retire here for that. So anyway, I'm really enjoying Florida. It hasn't gotten too hot for me yet. I did have a shop in Santa Ana, so I know what heat feels like. But they're all, this video is all some of the machines that we're doing. Made in Space is over 100 people now. When I started, it was 45 in January last year. They doubled. They're a 10-year-old company, and they just announced they merged with kind of merged with another company called Redwire. So Redwire is almost like it's an umbrella company. They're keeping Made in Space as a separate legal entity, and they bought another small company called Deep Space, and Deep Space has like 40 or 60 engineers with an enormous amount of space experience. These guys did like the Sun Explorer, the Jupiter Explorers and all that, interplanetary explorers. So they're a sister company for Made in Space now. And then there's a third company. So, and there's a deep pocket funding source in the mix that's funding all this. What their goal is to make the most powerful space company, that's not a big company like Boeing and Northrop and those guys and Raytheon. So they're making a very powerful company. It's really tremendous. That we just found this out like a week ago. So I'm having a lot of fun here, and the projects are fascinating. And they just gave me a G job. They just gave me a lunar rover thing that they're working on, and I'm going to design the control system for that in my spare time.
That's exciting, Don. A practical question for the before you send out the boards. I imagine you want to test putting something on it. We should probably think about whether we want to go down, now that we have the option of doing the sort of the Arduino tools or doing the SDK. We should figure out whether which one we want to do, so yeah, do reach out. We'll sync up on which path to go. But that's exciting.
As soon as I verify power and the board works, I'm sending you at least 2 boards.
Oh, goody.
Okay, you're the number one on my list because you're the one doing the software. And once you get Forth working, then our next, or the first Forth meeting that we have, monthly meeting, when we have Forth working, we'll give you guys a demo of this robot board, and we'll go from there. I have high hopes for this thing. Cost a lot of money so far, but that's all right. What else I got to spend it on? Any other questions?
Yeah, this is Andy Wright. I have another obligation, so I've got to leave the group now. It's been very interesting up till now, but can't stay. All right.
Hey,
Bye.
Thanks for stopping by, Andy.
Yeah.
I think
All
someone
right.
on the, sorry,
Go ahead, Sean.
I think someone on the mailing list mentioned that there was a ability to write code on your laptop and send it to the board.
Oh, of course. Yeah, you're gonna. So you can, if you just want to write C, I don't care. You install the Arduino IDE, and then there's a plugin for the ESP, and you can start writing C code for it if you want. Brad will have a downloadable binary that you can use the ESP programming tools to download the Forth onto it. So those are two methods
Got
to
it.
program the board. And I'm
Can you
using
write sketchy code for it?
yes, you can. I learned Arduinos when I came here. They used them a lot. I was like, what? Okay.
Well, in all these years, I've seen a lot of sketchy code, but they've just started calling that the last few years.
Yeah. Yeah, the Arduino interface is fully supported with the ESP32. So you can do some research on the web and get that interface installed, and then make sure you put the ESP32 plugin, the special plugin. And
Especially now we're off the ESP32 solo. Ah, well.
yeah. Oh well.
For those of you missing the context, we previously used a sort of an eclectic variant of the ESP32, and unfortunately, the software support wasn't too great in the IDE at that point. I actually haven't checked lately. Maybe somebody finally got around to it. But
Yeah, now that I designed it out, it figures.
All right, so it sounds like Don's pretty much done, and I'd like to thank him and encourage those of you who are listening and want to participate to contact Don. If you want to participate right away, great, send him money. If you want to participate later on, maybe send him money now and get your board when it's maybe a little further up the learning curve. And I think it's time to move on to John Peters.